Hey guys, today I will be showing you my implementation of the vision transformer. So first we have the normal imports. I have the standard Python library as well as Torch, PyTorch, which was the main deep learning framework I used, and save tensors for loading the checkpoints and training weights for my data. Then we can go on to the actual encoder itself. I have some logging here just for debugging. As you can see here, my model is actually training right now and the loss is going down, which is good. Here is the encoder class, basically the class that takes in the inputs and encodes them and creates embeddings so that we can train the model on those embeddings. Over here I'm using nm.sequential just for simplicity. Gallo is what introduces nonlinearity into the model, and I'm here using dropout to prevent the model from overfitting. Here I have the forward model, which actually lets the inputs go through and actually let the model create a prediction. And over here I have the QKV attention mechanism. It's also implemented over here. One of the main approaches that I had to re-implementing this model was using Einstein operations, also called INOPS. I'm sure you must have seen it in the imports. It basically lets you define or use this type of notation for your tensor transformations. And it's a lot easier than actually going through looking at the dimensions of the tensors and manually manipulating them for however you want, in this case for the projection methods. Then I have the normal attention mechanism, residuals, and feedforward. Over here we have the VIT class itself, which is the vision transformer class. As you can see here, we have the CLS tokens and position embeddings, which basically tell the model which position each patch is in. So how vision transformer works is it's basically very similar to the kernel method in CNNs, where you take patches of the image, and each patch is considered a token in the sequence. And since transformers are sequence-to-sequence models, you basically predict the next token, and in this case there's only one predicted token, and that token will be the prediction. So if it sees multiple patches and the patches tell it that it's a dog, the last token that it outputs will be dog, and we'll see that soon as well. Over here I also use dropout to prevent overfitting of the model, and the transformer architecture is initialized here, and the feed forward as well. As you can see, we're creating the embeddings, creating the CLS token, and passing it through the transformer to return the logits itself. Over here we have the load pre-trained weights function. This is basically for my sanity in testing, where I load pre-trained Hugging Face weights, so weights from Hugging Face, just to see if my architecture itself can run inference on weights that have been pre-trained, and everything works as normal. It's a little bit ad hoc because I couldn't get all the key value pairs quite right, but it still works, and we'll see that in a second as well. And yeah, these are basically just matching the keys in the dictionary from Hugging Face into the model architecture. Here's the main driving logic. So how I have it is basically a CLI tool where I can pass in certain arguments, use trained weights, evaluate image path, and it'll let you run the model. Over here, it'll use the trained weights, otherwise it'll just use the Hugging Face weights. Evaluate, it runs it on the test dataset of the dataset that I'm using called CFAR10. And image path lets you run inference on any of the images that you have that you'll see also. Over here we have the training loop. I initialize the model here. It's about 86 million parameters considering this initialization. I'm using cross entropy loss in Atom. I was considering using Atom W, but I thought that it was not really necessary as well. Then we have the training loop itself, 20 epochs like you can see here, and I checkpoint the data here and save the graphs. That was basically for my paper. Evaluate, like I said, evals the model on the test data set. Otherwise, it just runs it on the Hugging Face weights and normal inference. And that's about it. And these are the labels for CFAR10. Otherwise, it takes the labels from ImageNet, which is a much broader data set, and I have the usage here. So I'm just going to show it to you. If I run python.vit.py, it's basically going to run inference on this image right here based on PyTorch of a dog. The breed is a Samoyed. And so it's going to run inference, and let's see over here what it actually predicts. As you can see here, it's using CUDA, skipping these layers, and as you can see, Samoyed is 97%, and that is my model. Alright, thank you very much.